I managed my whole of my university education by avoiding halls of residence, actually, which I was pleased with. Okay, is there anything you'd like me to do in particular? I mean, as I said, these sessions are for you. Normally these lecture courses don't have problems classes each week. This is indeed because of the COVID situation that the department is offering these as well. So I don't have anything planned. I can do all sorts of things, I suppose. But it's a chance for you to say you didn't understand this or you didn't understand that, and please explain it again. Or I can go through some of the exercises that I set or do things similar to the exercises that are coming up. So if anybody wants to suggest anything. Well, whilst you're mulling that over, why didn't I just go through one of the exercises then? Sorry, was somebody about to say something? No, okay. Let's look at 1.6. It's line 462. I'll write it up, but it's useful. So what does it say? Okay, maybe I'll just try doing this here. Is that visible or is it too small? Nobody wants to venture an opinion. May simply be too small for you. Okay, can anybody, well, I mean, I put it here because, not because you don't have it in front of you, but now I can kind of point with my pen, that's all. So the idea is, so I'll continue until somebody tells me it's illegible or something. So what is this exercise saying? We've got a formula, and when I write V0 to Vn, I probably mean that V0 to Vn are all and only the free variables of the formula. Maybe just a subset of them are the free variables of the formula, but there are no more free variables outside of V0 up to Vn. So what we'll define is, we'll think of the formula as being perhaps defining a function on V1 up to Vn, which gives us some V0. So the function I'm defining, G sub phi, is going to work on an n-tuple y vector here. And what the function will do is tell me how far I have to look through the universe of sets to find an x which will witness this existential quantifier in front of the formula. So for some choices of y vector, there may not be an x that makes this true. But for otherwise, there will be an x. And that's what this little approximation, this wiggly equals, is. I think what it really should be, technically, is this. So maybe in next year's edition, I'll change this to that. And that just means, you know, if it's defined, then this is how to define it. So G of y vector may be undefined if there's no beta, because there is no x that'll make this true. But G tells us where to look to find an x. Oh, I say otherwise, it's 0. Oh, so maybe I should just, I take that back. Maybe I should just say equals here. It's always defined, right? It's going to be 0 if there's no such beta. So what it asks is for you to show that for all psi, if I look at G and I look at all the possible y vectors I could take from the xith level of the V hierarchy here, then the range of G on this V psi is a set. And indeed, well, the language that I'm already saying here is sort of giving it away. Because the axiom of replacement, one of our ZF axioms, says the range of any function on a set is a set. And well, okay, I've just defined this function here, G. So there's one function for each phi, like this. And this is a bona fide definition, right, which I can write out in set theory. So the answer to this first part here is rather short. It just says, you know, G of phi is definable as a function in set theory, and the axiom of replacement says the range of a function on a set is a set. And that's it, right? So it's just a simple application of the axiom of replacement. So it's almost a one-line answer there. Deduce that, and now there's a new function, f of sub phi of psi, and that just says the supremum of this here is a well-defined function. Well, what is this? We've just argued that G of phi here acting on sets gives me sets. So this G of phi here acting on a set is a well-defined function. And supremum is the same as the union. So I think my answer here would be to say that we may define f sub phi using the fact we've just shown by the axiom of replacement that G of phi on V psi, the range of G phi on V psi is a set, together with the union axiom, is a well-defined function giving me sets. So I think you just say, by application of the union axiom on what we've just seen, f of phi of psi is well-defined. So again, this is another one or two liner. You use the axiom of replacement on this part, and then you just say, I will use the axiom of unions to define f on this part. Okay, are there any queries? So quite a short answer there, but of course, it takes a bit of getting used to see what kind of thing we're appealing to here. But the giveaway here is it's asking about the range of a function on a set. So that's what flashes up to me that it's about the axiom of replacement. And supremum is the same as union. So this is the union axiom. Okay. Let me go through 1.7 then, unless anyone else wants something else. Okay, 1.7. Now this I said was the slightly silly exercise. But again, it gets us used to what the axioms are. So which axioms of ZFC hold in W epsilon? Where firstly, W only has got one element, the empty set. And secondly, when W is ON, which axioms of ZFC hold in ON? And I'm just reminding you here that we define less than on the ordinals as the same as set epsilon. Let's do ON first. It's slightly less silly than this empty set one. So which axioms of ZFC hold in? So my universe of sets is just this well-ordered class here. Okay, so we just go through and kind of tick them off. So axiom 0, this was the axiom of extensionality. So again, interrupt me if you want more explanation. So this holds in any transitive class. Any transitive class. Because a transitive class has no epsilon holes, so it knows all the atomic facts about its sets. And the point is that ON is a transitive class. Any element of ON is a subset of ON, because any element of ON, any ordinal, is the set of its predecessors, which are all ordinals. So alpha in ON means alpha is a subset of ON. So this holds. I don't remember the numbers offhand. The empty set. This also holds because 0 is the empty set as an ordinal. So a reasonable answer to this is just literally just a list down here with some ticks and crosses and some reasons. Right? There's no need to write a whole essay about this. Here's another one that holds, infinity. This holds because omega in infinite set is in ON. And so does the axiom of foundation. If I've got a term here that's contained in the universe under discussion, and it's not empty, there's an epsilon minimal element of A. Indeed, there's a least element of A, because this is a strict total ordering. It's not just a partial ordering. So an epsilon minimum of A, which is the least ordinal in A. So this one holds. consider the axiom of union. Well, if X is an ordinal, then actually union of X is an ordinal. Union of X is the same thing for X a set of ordinals, for X contained in ON. Union of X is the same as sup X. And this is the least ordinal greater than or equal to every element of X. So the axiom of union holds. It's an ordinal. But then some simple axioms fail. Axiom of pair. Okay. This isn't going to hold. 0, 2 here, this is not in ON. 0, 1, this is in ON because it's 2. But 0, 2 is not in ON. Right? So this fails. So now some things become a little bit silly. What about the axiom of replacement? Well, that's stated as saying, you know, if I've got a term which is a function, then that function, if I can define a function, something that's a function on the class ON that's concerned here, then the action of that function on a set is always a set. But what does it mean for something to be a function? A function is a set of ordered pairs. Right? First thing, second thing. Input, output. So if f is a term, and f as defined in, well, ON is W, and if this is a function, then it's a class of ordered pairs. But actually, in ON, there are no ordered pairs. So actually, what we've got, actually, the only function that's definable, right, if you like, is the empty function. Right? Because the requirement that something is a function is that it's a relation and that the relation is single valued on any ordered pairs in the relation. Well, that requirement is satisfied by the empty set. It's a relation, right? And any ordered pairs in there, blah, 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 blah. That's always true vacuously because there are no ordered pairs in there. Right? So the empty set is always a relation, logically speaking. The empty set is always a function, logically speaking. And the action of this function here is the empty function. It does nothing. So this here is trivially the empty function. And the action of the empty function on any set produces me the empty set. So this is the only conceivable function that I've got to verify the axiom of replacement for. Right? And the action of this function on any object in the universe of W here, okay, is a set in the universe. It's the empty set, which is there. So this here is a function, right? And when it acts on a set, it produces a set. So the axiom of replacement holds kind of trivially or vacuously. This is the only function to worry about. So some people don't like this, but it's just a question of how we've logically laid out our axioms. Right? And what about the axiom of power? Power set axiom. So let's take a member of our universe, alpha. What is the power class of alpha? By definition, this is the collection of x's in W such that X is a subset of alpha. Okay, so let's just inspect. And what do we see? Alpha is an ordinal and it's transitive. So any of its elements are subsets. But the only things in W there are ordinals. So the only things I can ask about here, which X's in W are subsets, it's the same thing as asking for a collection of ordinals such that X is a subset of alpha, which is just the collection of ordinals such that X is less than alpha. And this is just the collection of ordinals where X is a member of alpha. So actually, this is, less than or equals. I stepped up there. Right, because alpha is a subset of itself. And what does this amount to? This is all of the ordinals up to alpha together with singleton alpha. So this is the successor of alpha. This is alpha plus 1. So officially speaking, power set of operation applied in this pretend universe just returns the next ordinal. Okay, and that is a set in our universe. So the axiom of power holds by this reasoning. Okay, a couple more to go. Axiom of separation. So we say something like let B be a term, and I've got some set in my universe. So this is just an ordinal here. For the separation axiom to hold, we need that Z intersect B here is an ordinal. And this fails. I'm just trying to think of a simple enough example. Let's just say let Z be 2. Right? So it's just the ordinal 2, which is just 0, 1, remember. And let B be the collection of ordinals in Z such that Y is not the empty set. Okay, this is a perfectly good term. Sorry, well, B, let B, I don't need to write this bit yet. Let B be just, this is a proper class, anything that's not 0. And now, what is Z intersect B? Z intersect B, in the non-zero things in Z, it's this set. But this is not an ordinal. It's not in our universe. It's just the singleton set 1. So here's an example of the separation scheme failing. So this fails. And lastly, axiom of choice. So again, I think this is kind of vacuously going to hold for kind of silly reasons. So what is the axiom of choice? It says if you've got a function and the domain of the function is a set, and F always returns non-empty sets, so I can say the empty set is not in the range of F. Again, it's an if-then. Then something has to happen. This Cartesian product here of F is non-empty. So I'll just remind us what that is. Pi F, this is the collection of functions G, where the domain of G is the same as the domain of F. And for all x in the domain of, well, either F or G, G of x is a member of F of x. So it's a choice function. It chooses an element from each of the sets that F enumerates. And that's why we specify f has to be non-empty. Each f of x is non-empty. But we saw before that the only function we had in this toy universe is the empty function. Definable in W. So now then the question above is, well, I mean here, just wondering whether I've said exactly the right thing in my so, okay, I think it's fine. So when I say, so the empty function is indeed a function. Its domain is trivially the empty set, right? So that's 0, that's in our universe. And indeed, 0 is not in the range of the empty function. There's nothing in the range of the empty function. In particular, 0 is not in the range of the empty function. So actually, with the empty function, this is all true. Okay, so if this is all true, what about this? Well, the product here of the empty function is, well, let's just try and see what possible g's could we have in here. Sorry, this should have been function. So I look at the possible functions whose domain is the empty set, right? So it's just going to be the empty function here, right? And now there's some condition about all of the things in the domain of the empty function. Well, actually, there's nothing in the domain of the empty function. Right? So this is an empty condition. To work out the truth value of this, we only need to work it out if x is in the domain of the function. Well, there's nothing in the domain of this function, so this condition is without any power or any restriction. So actually, the empty function is in there. Okay. But this is the number 1, right? And this is in, which is an ordinal. So kind of vacuously, the axiom of choice holds. If you're being, strict and pedantic about this. So that holds there. Okay, do you want to ask anything about that?
I have a question about exercise 2.2 that you said.
Okay, sure. Okay, go ahead.
I was going to, I'm trying to, it's proving that their cofinalities are equal. And I'm trying to do it as a two-way, like this is less than this, and then do it the other way around so they come out as equal.
Yes.
but I can't seem to show that the cofinality of, hold on, I can't show that the cofinality of alpha is less than or equal to the cofinality of beta. And I was wondering if you could just give a hint in what direction to go in, like what function I could define to prove that.
Okay, so we're looking at 2.73 there. Okay, so I've got f is cofinal from alpha into beta, and it's strictly increasing. Then the cofinality should be the same. Okay, so what have we got? We've got alpha and beta here. I've got this cofinal map F. Sorry, I'm going off the page. F here. Okay. Oh, it's an increasing function, right? And we want to show the cofinality of alpha is the same as the cofinality of beta. So here's the cofinality of alpha, and here's the cofinality of beta. And these better be the same thing. So you're saying that you've got this one way round, but you can't do the other way around. Which way was successful?
I think I've managed to show that the cofinality of beta is less than the cofinality of alpha.
Okay. And you want the other way around, right?
Yeah.
Okay, so let's suppose we've got strictly increasing functions witnessing this cofinality. We've got a G that goes from cof alpha into alpha, and we've got something that witnesses the cofinality of beta is cof beta. So there's some function unbounded into beta here. And let's give that a name. Let's call that H. Right. Now you want to show you want the cofinality of alpha to be less than the cofinality of beta. Right, so it will be enough to find a function that is cofinal from this ordinal into alpha. So it's enough to show that there is a function k, say, that goes from cofinality of beta cofinally into alpha. Right? Because then, sorry, this is cofinality of beta into alpha. Because this would imply the cofinality of alpha is less than or equal to this. Right? Because cofinality of alpha is the least domain of a function that's cofinal into alpha. Okay, so it has to be less than or equal to this. Yeah. Okay, so we now need a trick to find a function that's like that.
That's the bit I don't
That's
know
the
where
bit
to
you can't
start.
get. So
With that
I'm trying to think how to
exactly.
give you a
Got
hint
few
without giving
random.
you the answer.
Yeah.
Well, I know
I
that
was trying
this.
to do a map from.
Go ahead.
Sorry, my Wi-Fi is really bad.
Oh, I'm sorry.
Yeah, I was trying to combine H and like an inverse of F somehow.
Yes. Yeah. That's very close, actually.
Yeah, I was just saying. I was originally trying to find. Oh yeah.
Yeah, that's very close.
Okay. Yeah, I think what it is, I can't prove that map itself.
So you can't prove that map.
Final.
You broke up there. Sorry, the sound broke up.
Yeah, I'm struggling to show that map itself is cofinal.
It's cofinal, right? So, I mean, let's see. You need to use the fact that all of these functions are strictly increasing, right? So let's see, where would we send some ordinal delta here, right? So H will send delta up to some H delta here. And I now want to, I know that this F function is cofinal into beta. So I know that there are going to be, say, some Tor over here. We know there is Tor less than alpha, such that F of Tor is greater than or equal to H delta, because F is cofinal. Into beta. So what I could do is just take delta to the least Tor such that F of Tor is greater than or equal to H of delta. So I suggest you consider the map from from delta to the least Tor such that F of Tor is greater than or equal to H of delta. So that's my hint. That's the function to look at.
All right, thank you.
All right, and yeah. So there are a few minutes, a couple of minutes left. Wondering how to do the time. We haven't quite done fixed points yet, so.
Could I just ask a
Yes,
question about the exam this year then?
Okay.
Are you because it's now all it's open book? Are there going to be? I assume there won't be any define this sort of questions, or
There will be less of that. I won't say there's none of that, but it makes sense to have less of that if it's open book. I mean, just asking people to copy out definitions is a bit kind of pointless.
I know that was the beauty of the last exam season.
Yes, I know. I mean, it was, it gave away some easy marks, for people to do.
Yeah.
So it's going to be a bit different. I haven't decided exactly what it's going to be like. There will be something. Yeah. So don't anything I say now you shouldn't hold me to, but because the exam isn't set yet. What I
Okay.
Yeah, I don't want to say too much because I'll be holding hostages to fortune, and you should ask me that question in a few weeks' time, and then I can kind
All
of
right.
give the game away then, rather than say something now and then it'll be false. But you're right; it's going to rely less on parroting out bookwork definitions. But it might ask, for example, to you to kind of summarize.
And so I assume like there'll be less proof. Yeah.
Sorry, you broke up there. I didn't
Okay.
hear. Could you say it again? Or
No, what you said exactly what I was asking.
right. I mean, of course, I'm going to say something near. I mean, certainly by the end of the term, if not earlier, about that, and just try and give you a bit of guidance there. Right.
All right.
Of course, we've had. I mean, I'll just say as some just asides. So over the summer, actually, there's been lots of kind of workshops and things for lecturers like us. I mean, not in the university, nationwide, actually, for mathematics lecturers. And you know, how to turn your course into something that's online. And one of the afternoons was about assessment and exams in open book, turning your exams into an open book exam. And somebody who'd had a lot of experience on this said actually they changed their exams into an open book format. And he found in the end that actually it didn't make a lot of difference, right? In a way. So just changing the course to remove just some of the most obvious bookwork definitions and devising some examples there. And they found overall that the the overall profile of the the scores that people got were not a lot changed. So what the lesson that was drawn from that was that this shouldn't have a radical effect on the overall score or curves or so on of the sorry, I could have turned my face back on again. I mean, this didn't have an overall big effect on the the curve of the distribution or the scores that people got if you devise the exam in an appropriate way. So the idea may worry you, but it doesn't worry me. But of course, you could say that, I mean, actually, I always worry about my exams, right? I mean, I think I worry as much about the exams as the students do. Because, the last thing you want is an exam that people can't do. And, everybody then is just angry and frustrated. So I think in the past, my exams have not been so hard, right? But I do worry sometimes in case that they are too hard for some people. But I think, in the past, it's sort of worked out fine. And I think what I'll do is just, in a way, tweak the exams questions to just remove the obvious parts about the bookwork stuff and put something else there instead. I mean, that's kind of my intention at the moment. So I won't say anything more concrete than that at this point. Okay. Time's up unless you've got any other queries for now. Okay, so this will I'm hoping to get the uploading of the recordings to work a bit faster, but I have terrible internet, but I may get some better fiber broadband next week. So, but basically these will get uploaded overnight. And so this should be here for your friends to look at if you don't want to look at them by tomorrow. And there will be by Monday. Again, the next lecture will be recorded and put up there. Okay, fine. Otherwise, I'll say goodbye then, if there's nothing else to ask. So, okay, have a good weekend.
Thank you very much.
Okay,
Thank
bye.
you.
Thank you.
Bye.